So welcome to Math 150 Multivariable Calculus. This is, I believe, lecture 21. And what we're going to be doing today is we're going to be talking about Monte Carlo integration. And then as time permits, maybe talk a little bit more about polar integration and maybe symbol regions. So this is the 21st century. I showed you the example last time where Mathematica was able to handle the really bad double integral, giving it in the wrong order. Mathematica still solved it. And Mathematica even has the more general, hey, just implicitly define the region and I'll figure out how to integrate over it. Absolutely amazing what can be done. So given that there's so much powerful computing available now, with so much wonderful symbolic processes, I really want to do a couple of application lectures. What can you do? What do you do when you have an integral that's so bad that you can't find a closed form expression for it? So you have to somehow approximate the integral. Well, how would we approximate a one-dimensional integral? What would we do? So how do we do one-dimensional integrals? How do we approximate? Yeah, Riemann sums. So, you can choose how you're doing the endpoints and whatnot, but we were doing, something along these lines, and we could do something like this to find the area under the curve. If I give you something in a 360-dimensional space, this is going to be an incredible challenge to do. So the idea is you have some region A where it's easy to tell if a point X, say X1 to XD, is in A. And we'll say A lives in a box. For simplicity, let's assume it's 0, 1 to the D. So this is the D-dimensional hypercube. What should the volume be of the D-dimensional hypercube? 1. And so when I have some region A and I'm trying to calculate the volume of A, I'm asking what fraction of this hypercube does it fill up? So a natural question you could ask is, if you draw the biggest hypersphere possible in one of these boxes, what is the ratio of the volume of the hypersphere to the volume of the hypercube? You might not want to do a unit cube. What might you want the side of the cube to be? If we're trying to compare it with a sphere, rather than having a cube of side length 1, what might you want the side length to be? 2R, or we're going to make R be 1s, we just have it as 2. Because we know the volume of the cube is going to scale up like R to the D. The volume of the sphere is going to scale up to R to the D. We might as well take the radius to be 1. So we should probably use the cube going from -1 to 1, something like that. And you can ask what fraction of the cube is covered by the sphere, what fraction of the hypercube is covered up by the hypersphere. This actually has a lot of applications. This is related to sphere packing. How many spheres can you put in a certain dimension in space? This is related to error detecting codes. There's a lot of wonderful applications of this. I think one of the videos talks about the gamma function and trying to calculate the volume of the n-dimensional sphere. So there are ways to do this. You need to use d-dimensional spherical coordinates. So for those of you who are already enjoying spherical coordinates, what now? But there's so much symmetry in this problem, you actually don't need to explicitly know what the d-dimensional spherical coordinates are, and that makes things really nice. Let's talk about the general situation. So we'll start off in the plane. So I have some set A. All right, and now I'm going to start choosing points. And maybe some of the points land inside of A, and some of the points land outside. And I'll use 2 different colors just to make it easy for me to tell which ones are inside and which ones are outside. So imagine we have n tosses uniformly in the box. Say n sub A land in A. What might you estimate the area of A? Anybody have any thoughts as to what you would estimate the area of A to be? N sub A divided by N, or N sub A over N times the volume, which in this case is 1. And so I'll put the volume there just for explicitness. But if we choose the volume to be 1, then it's just what fraction of the points land in. And this should be a really nice way of estimating. Now, if you're going to do this, what do you have to be able to do? If you want to use this method, what do you need to be able to generate?
Random points.
Random points. What kind of random points? They've got to be uniformly spread. They have to have equal chance of landing everywhere. Anybody ever see the TV show Press Your Luck? So years ago, somebody won over $100,000. This was back, I think, like the 1980s. It was unheard of to win that much money. For years, they would not replay this. And they initially refused to give the person money, and then they had to give them money. So the way it works is you have a little game board, and you have little lights that go around, and you say, stop. And if it stops on money, it adds money to your account. If it stops on a whammy, you lose everything. Some of them is money plus a free spin, which means you get to keep going. You get to keep going until you have no more spins. There's other rules. And so the lights move randomly, and you have to try to time it so it's going to land on something that is worth a lot to you. Well, somebody recorded a bunch of episodes and watched them carefully and noticed that the light wasn't moving randomly. And figured out what was the pattern. And so you could actually see him smiling because he knows exactly when to press it. And so he got over $100,000. And it was not random. So then they had to change their procedure as to how they generate things. There was a Canadian lottery years ago where they thought they were generating things randomly, and a Canadian geologist said, no, you're not. And they said, no, yeah, we are. And so he took 20 scratch tickets and said, scratch them in the following way, and you'll win. And he was right on 19 of 20 of them, which, oh, okay, we will listen to you. Choosing things randomly is not always easy. If I choose one of you and ask you questions, are you a typical Williams student? Or does it depend on what the questions are? If I ask you where you're from, do you think you would be a representative set? Or do you think people taking Math 150 might not be representative of Williams in terms of geography? Or in terms of class year? 150 is taken more often by freshmen, sophomores than by juniors, seniors. So there's very easy ways to have things that seem random that actually have biases built into them. So choosing something, generating something randomly is not easy. One thing we can do is hopefully toss a coin. On, off, yes, no, 0, 1. And so if you toss a coin, we can write numbers in binary. So if I toss 10 coins, if the first one is a 1, I move a half. If the next one is a 1, I move a quarter. The next one is 1, I move an 8. And so that would give me binary numbers. And so I would not be choosing numbers continuously from 0 to 1. But I could, if I do enough tosses, if I do 10 tosses, that's 1,024 possibilities. If I do 20 tosses, that's a little bit over 1 million possibilities. That's pretty much good enough for what I'm doing. And so we just toss things randomly. It turns out that if you really get into stuff like this, there are better things to do than choosing things randomly. There's choosing things quasi-randomly. Anybody ever read Rosencrantz and Guildenstern of Debt? It's supposed to be a liberal arts college, There's enough people. Okay. So in this book by, I believe, Tom Stoppard, you have two people who are tossing coins throughout. And at some point in the book, they had over 90 consecutive heads in a row. What is the probability that the next toss will be a head? What do you think? One possibility is 1/2. Why?
Because it doesn't matter the previous coin.
Sure. What's another probability for the next toss? 100% or something very close to 1. Maybe this coin is not fair. At some point, 90 plus, heads in a row. Maybe this is not a fair coin. And so maybe I start to update my probability that maybe it's not fair. So, it's really important to be able to choose things, randomly. It is possible we could have a tremendous amount of bad luck and get a huge number of our points just clustering down there. And if that happens, our estimate's going to be off by a lot. So one way around this is to actually have ways that uniformly construct points throughout the region. And as you add more points, it uniformly adds the points throughout the region. And there's ways to do this using the Fibonacci numbers. So the Fibonacci numbers actually have applications for sampling and doing integration. Now, do you think it's likely, as you take more and more points, that you're going to have really bad clustering? So the solution is the more points you do, the less likely you are to have clustering. And this is where probability comes into play. Has anybody done anything probability like? This should be at least a little bit in pre-calculus where they talk about some basic probabilities. Have you seen or heard of the central limit there? That if you do a process again and again and again, and you look at the average value, it's typically going to converge to being normally distributed or bell curve or Gaussian. Whenever you have this many words, it's important, centered at the true value. If I choose the points uniformly in this box, what is the probability I land in the area A? So probability land in A is what? So what would be the probability I land in A if I choose my point randomly?
A over the entire area.
I'm sorry?
A over the entire area.
Area of A. Right. A is a set. So area of A over the area of 0, 1 squared, which for us is just the area of A. So if we do n tosses, how many do we expect inside? So if your probability is area of A and we do n tosses, how many would you expect? Yeah, n times the area of A. And that's going to be our NA. And then the error is of size square root of n. So that's where you use some probability that the error is of size square root of n. Okay, so then our guess for the area is NA over n with error of size square root of n over n. As n gets large, what does square root of n over n go to? 0. And so this should converge to the area of A. As we take more and more points, this is going to converge to the area of A. And the place where you use some advanced probability and some advanced analysis is to say that the error is of size square root of n. This is the central limit theorem. And this is what makes the whole method work. So as long as we can easily tell if you're in the region, we can now use this to estimate the areas. Or if we were in 3 space volumes, all we have to be able to do is determine, are we in the region? I don't care how bad the region is. I just need a simple way to tell me, am I in or not? Right. So you should have watched some of the videos for this. Let me share screen with the mathematical code. Okay. So I've chosen, a couple of points. This is the first 20 points of a random sample. And if you're inside the set, it's marked red. If you are not in the set, it's blue. Does this look like a nice shape at this point? It's not really clear with just 20 points what's going on. If I go down to 5 points, so let me try to just play it. Let's see what happens if we add more points. As you can see, as it's adding more and more points, it's filling in, and it's writing at the top the area estimate. So at this point, I think we should be able to identify what shape this is. Just for the record, because this is being recorded. Circle, right? So this is becoming, you know, circle. And then if I go all the way to the end, now, I don't know why it's going into a more lighter color, but you can see the circle. Now, if you look at it, the blue points are definitely clustering outside the circle, and the red points are clustering inside the circle. Why do you think that is?
Well, I mean, they're both the same set of points. That's kind of weird.
Yeah, I'm just choosing the blue points to be, you know, anything outside the circle, I'm just coloring blue. Everything inside the circle, I am coloring red. Do we see any clusters of points among the reds or among the blues? So let me take a snapshot of this. So here's my set. When you look at this, do you see any places where it looks like, oh, you can't see this because I have to stop the share and restart the share. Sharing is caring, as my niece would say. Okay, so if we look at this, do you see any regions where it looks like we're missing something? Are there, you know, deserts of points among, you know, the red and the blue? Make it a little bit larger. So if I look at it like over here, that's a pretty big area where there's not that many points. It's basically like 1 point in the center, maybe 3 points. Right? Do we agree that it looks like there's a bit of a desert? And so you can ask, how likely is it to have deserts like this? The more points you have, the smaller the deserts could be. If I go back, just a second. So here's, you know, far fewer points. Do the deserts look bigger here? You know, here we've got a, you know, pretty good size, you know, desert, you know, right over there. And so the question is, you know, over here, again, there's a bunch of, you know, deserts like this now. As you take more and more points, these are going to become less and less important. But it is an issue. What if you get extremely unlucky? Looking at this, it looks like the deserts here are definitely much smaller. You know, there's still going to be a few big ones. I've got a good one over there, which might remind you of a, you know, geometric shape from movie history. But the more points I have, the less likely I am to have a good sized desert. And as long as my region is not too strange, I should be okay. And so this should allow me to figure out what's going on. All right, for the next one, let's go back. So again, with 20 points, it's really not clear what's going on. But as we start adding more and more points, you know, the figure starts to emerge. And at this point, you know, it's looking a lot like an ellipse. And when I get to a huge number of points, I have about 1.61. And so the ellipse has a major axis of length 2, a minor axis of length 1. So A for this is going to be 1, B is going to be 1/2. And we could then try to figure out what is going to be the equation for the volume or the surface area, oh, sorry, for the area of an ellipse. Can we figure that out from over here? Well, this is where you can start to do some numerical mathematics. I'm doing the ellipse where a equals 1, b equals 2, or so b equals 1/2. Maybe we can do a couple of them and try to figure out what the answer might be. So what you could do is you could do like area of ellipse. You could have your A, your B, and your area estimate. So when we had A equals 1 and B equals 1/2, we had about 1.61. Anybody want to guess what 1.61 might be? Pi over 2. So what might you conjecture the area of an ellipse is as a function of A and B? This is just one data point. So we had x over A squared plus y over B squared equals 1. The area conjecture is what? Yeah, pi times AB. Now, is there a special case where you can test the conjecture where you know the answer? Circle. Good. If A equals B equals R, get pi R squared. So this formula at least reduces the formula for the area of a circle in the special case when the ellipse is a circle. And it seems to generalize. If I have an almost circle, if say A equals 1 and B is close to 1, then the area should be close to pi. So this is a very reasonable formula. And then we can talk about how would we try to prove this. So we want to integrate over the ellipse with the function 1 dA. So if we have x over A squared plus y over B squared equals 1, this is the boundary. So here's A, here's B. Do you want to integrate first with respect to x or first with respect to y? So do you want to fix x and let y vary, or do you want to fix y and let x vary? It does not matter at all. That's why I'm willing to let you make the choice. Because it would make my life painful. I'm then going to do some leading questions. So we'll fix x. So if we fix x, then we have to figure out what's the range of y. So y is going from minus the square root of 1 minus x over A squared, and we have to multiply that by B, to the square root of 1 minus x over A squared times B. So this would be, the integral x goes from minus A to A, integral y goes from minus the square root of 1 minus x over A squared times B, square root of 1 minus x over A squared times B, 1 dy dx. The y integral is not going to be a problem at all. The x integral will be a little bit of a pain. By doing some change of variables, you can see that the integral is going to be some nice number times AB. So with a little bit of work, you can see that it's going to look like something times AB. We don't know what that something is. Well, we know what the something has to be in the special case. Well, let's actually do this. We've got some time. So this is going to be the integral x goes from minus A to A. I'm going to pull out the B. I'm going to pull out the 2. We have the square root of 1 minus x over A squared dx. Let's let u equal x over A. So du is going to be dx over A, or dx equals A du. As x goes from minus A to A, where does u go from? So u is x over a. As x goes from minus a to a, where does u go from?
-1 to 1.
Negative 1 to 1. So this would just be equal to 2b integral u goes from -1 to 1, the square root of 1 minus u squared. Dx is going to become a du, so I can put the a here, du. So we just have to do this integral now. Notice this integral is independent of a and b, right? Do we know any choice of a and b where we know what the area is?
When they're equal.
When they're equal. So if a and b equal 1, we know the area is just pi, right? So what does this integral have to be? Has to be pi over 2. So this has to be pi ab, as the integral is independent of a and b and is pi over 2 if a equals b equals 1, as circle area is pi. So we actually don't even have to do that integral. We can get the area of the ellipse just by knowing the area of a circle. Another way of doing this, and this is the one that's done in the video, is going through the change of variables. And so the way we could do that is, when we look at x over a squared plus y over b squared equals 1, we see an ellipse. An ellipse is really what kind of shape? It's a circle if you adjust your units and you don't measure the same units along the x-axis and the y-axis. Normally, this is not a good thing. Anybody know about NASA's, I think, $25 million blunder on Mars a few years ago? There's, I believe, a probe that was getting ready to land, and everything was in the metric system except one subsystem, which was doing things in the English system. And so when it passed its output onto the rest of the programs just assumed that it was coming in the metric. And so it miscalculated how much thrust was needed for the landing, and you ended up getting, I think, a $25 million crater. So you've got to be extremely careful with units. It's usually a very bad idea, but as long as you're clear and you describe what you're doing. Anybody here doing physics? If you see special relativity, you might see you have your x, your y, your z, your spatial dimensions, and your time dimension. And we often don't talk about time, but we talk about the speed of light times time. What's the speed of light times time? What units is that? Well, speed of light is meters per second and time is in seconds. So speed of light times time is what? Meters. It's a measurement of distance. And so if you look at c times t, it now has the units of time being the same as the units of the x, y, and z. So the other way of doing this is if we want to integrate over the ellipse of 1 dA, or integrate over the ellipse of 1 dx dy, I have x over a squared plus y over b squared. Let's equal to 1. That's going to give me my filled in ellipse. I could let u be x over a and v be y over b. So now I get u squared plus v squared is less than equal to 1. What kind of shape is u squared plus v squared less than equal to 1? What will that be? Filled in circle. And so now I would get du is dx over a and dv is dy over b. So dx dy equals ab du dv. So now the integral over the ellipse of 1 dx dy, when I convert, is the integral over a unit circle. What does the function 1 become as I change from x's and y's to u's and v's? Yeah, it stays the same. It's still just function 1. And then dx dy becomes ab du dv. So this is very similar to the calculation we just did a moment ago. Unit circle, du dv. So what is the area of the unit circle? It's just pi. And so that will give us pi AB. And so this is a really nice change of rules. If I gave you a ellipsoid, so I had x over a squared plus y over b squared plus z over c squared, what would its volume be? So volume ellipsoid. Anybody want to conjecture what this should be without even doing all the calculation? Yes. 4/3 pi ABC. Yep. Okay. Any questions about this? So Monte Carlo integration is a very nice way to do high dimensional problems, so long as you can easily tell if your point is in the region or not. If you can't tell if your point is in the region or not, it's not helpful. And then you want to get some estimate as to what is your error. And there's two possibilities here. One is just, well, given my estimate, what's my confidence interval? Where would I say the true value lies? And the more points you take, the tighter that's going to be. And then you have to decide, well, how unlikely is it that I happen to get something that's just completely absurd? The more points you have, the less chance that is. This is one nice advantage of using grids related to the Fibonacci numbers, is it makes sure that you don't have any particularly bad clustering. It really spreads things out uniformly. All right. What I want to talk about now is iterated integrals. And so basically, I want to talk about simple regions. So you're horizontally simple if the following is true. As you walk horizontally, you enter the region, stay, leave, and then come back. If walk horizontally, you enter region, stay in region, leave, and then never return. Vertically simple is similar. And then, of course, both is horizontally and vertically similar. Simple. So, for example, if I give you something like this, it's going to be horizontally simple. I enter, I stay in, and then I leave. This would also be vertically simple. Can somebody give me a region that is horizontally simple but not vertically simple? Yeah, I was actually just thinking that, and what song was in my head? Oh, this is bad. Nobody knows? Now, what starts with the letter C? No. Sesame Street Cookie Monster? C is for cookies. Right. So if I give you something like this, this will be horizontally simple. I come in, I stay, and I leave. But if I come in over here, I'm in the region, I then leave the region, and then I come back and I'm in the region again. So C is not vertically simple. It is horizontally simple. So when you're trying to decide which way to integrate, one possibility is, let me do the integration, first fix X and first fix Y and let X vary because it's horizontally simple. And so we would have two bounding curves. So we would have Oops, I'm gonna do this one. So we would have this and as our bounding curves. So again, what am I doing? I'm fixing a y, and then I have my initial x and my final x. So I could call this y1 of x, and I could call this y2 of x. And so I could integrate y goes from, say, y initial to y final, and then x goes from y1 of x to y2 of x, and then my function f of xy dx dy. So this would be how I would do the integral. And I have two very nice boundary curves, y1 of x, y2 of x. If I wanted to try to do this the other way, if I wanted to fix x and integrate with respect to y, this would be a challenge because I leave the region and I come back. So one possibility is to say, I'm not going to do it vertical. And I'm going to do horizontal. I'm going to fix a y and move horizontal. I'm going to do the x integration first. If you really don't want to do the x integration first, maybe the y integration is easier. What could you do? So is there anything related to this that's vertically simple? Yeah. What I could do is I could split it. Oops. I could split it here and have two different regions. And so now I would have one region would be this, and the other region would be that. Two vertically simple pieces. It's the sum of two vertically simple regions. So even though it's not vertically simple, I can decompose it as a sum of vertically simple. So as a rule of thumb, I would much rather do a lot of easy problems than one really hard problem. So this is normally a good trade-off. So rather than doing a hard, difficult problem that's not vertically simple, I can now just break it up and I'll just do two problems. And so here, oops, this was just the code for the integration. We just add. So if I give you something like this, then I have as my two curves this and this, right? Because if I'm looking at what's going on now, I'm going up like this. And so here, this would be, I'm choosing a value of x and then y goes. So this would be y equals, so I'm choosing a value of x. So y is equal to just want to make sure I use consistent notations. Over here, we said x went from y1 of x to y2 of x. So now I want x. So here, which am I integrating first, x or y? Y. So have y goes from something to something, and then x goes from maybe the initial value of x to the final value of x. So y is going to go from some function x. So let's do, b of x for bottom and t of x for top. So I'm going to go from my bottom value to my top value, and then have my function f of x, y, dy, dx. I think this is maybe better notation to use, bottom and top. Try to just really highlight what we're doing. And if we're using bottom and top here, what should we use for the other one? So if we're using bottom and top when we're doing vertical, what should we use for the other one when we're doing it horizontally? Yeah, left and right. So if I have something like this, this would be, left of y and right of y. So now we would have integral y goes from the initial value of y to the final value of y. X goes from the bottom value, the left value of y to the right value of y, f of x, y, dx, dy. So probably using left and right, and then, top and bottom is a good way to just really highlight where everything is. So let's try to do a problem. So let's say I give you some function. Let's say I've got the function let's say I have the curves y equals x squared and y equals x cubed from 0 to 1. So which do you think is the top curve? Which do you think is the bottom curve? Is it x squared or x cubed? Which one is larger between 0 and 1? X squared. So if you're ever not sure, just take the point. Take the point 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. Okay. So x squared is going to be the larger. So this is going to be, y equals x squared. This is y equals x cubed. So if I want to do the integration like this, which am I integrating first, x or y? Y. So x is going to go from 0 to 1. Y is going to go from the bottom curve to the top curve. What's the bottom value? So b of x is going to be what? What's the bottom curve? X cubed. And what's the top curve going to be? It's going to be x squared. F of xy dy dx. And now we just have to do the integration. So depending on what function I give you, we then just go through and we try to do it. We could, of course, try to do it the other way. And so now we could be doing it this way. So now which do we integrate first, x or y? So which one is being integrated first? X. So we'll figure out what x is in a second. Y is going to go from 0 to 1. And now we need to figure out the left and the right. So the left is from y equals x squared. Okay. So given a value of y, we need to figure out what the corresponding value of x is. Right? Before we had y as a function of x, that gave us the x cubed to the x squared. Now I need to find x as a function of y. So if y equals x squared, what is x as a function of y?
Plus or minus Square root of y.
Okay, so which do you think it is? Do you think it's the plus or the minus square root?
I guess it'd just be plus.
Yeah, it would just be plus from how we have it. So this implies x is the square root of y. So the left function as a function of y is just the square root of y. Everybody comfortable with that? This is the hardest part of the problem, is figuring out what the bounds are. Now we need to find the right. And so the right is from y equals x cubed. So if I want to write x as a function of y, what would it be? So if y equals x cubed, how would you write x as a function of y?
That means that x, or x equals to y.
It would just be y to the 1/3. And so now we would get the right bound is just y to the 1/3. And we would have a function f of xy dx dy. And so that's all there is to these problems, is you just have to figure out what are your bounding curves. And depending on what curves you have, it could be a real pain. My son was trying to do a calculus problem last night, and the curve just didn't look right. The book said, which of these points is the maximum? And none of them were candidates when he plotted things. And then I plotted it on my device using Wolfram Alpha, and I got a different answer than he got with his graphing calculator. And I said, what units are you using for your trig functions? He goes, yes, when I do pre-calculus at school, I do everything in degrees but as soon as you do calculus, what should you be doing things in? Wait, you've got to be very careful, watch for something like that. So always be aware of how people choose to define and orient things. This is particularly important when we do spherical coordinates. So for spherical coordinates, we have a sphere like this, and we have the radius rho. Then we have, so this is x, this is y, this is z. We have the angle coming down from the z-axis. And in a math department, that is phi. So phi comes down from z-axis. And phi goes from 0 to pi. And then theta spins in plane parallel to the xy plane. So 0 less than equal to theta less than equal to 2 pi. In physics departments, they often have theta as the angle coming down from the z-axis. Why do we do this? Well, the reason we do this is we want to be able to use polar coordinates. And in polar coordinates, what do you use in polar coordinates? What are the variables in polar coordinates? R and theta. And so if we are coming down, from the sphere, and we come down to here, and this is rho, and this is angle phi, then what is this length over here? What would that length be? This is just going to be rho sine phi. And over here, this is rho cosine phi. So we would get z is rho cosine phi. We let rho sine phi be r. And now that gives us polar coordinates in a circle of radius r above the xy plane. And so now you use polar with r equals rho sine phi and theta. So now x would just be r cosine theta, which is going to be rho cosine theta sine phi, and y would be r sine theta, which is rho sine theta sine phi. And then for later, we have to figure out how does dx dy dz transform to d rho, d theta, d phi. What goes in here? Can anybody quickly tell me part of what has to go in here? You know, at least part of it. It's 10:50. We've got to answer this fast. What are the units of dx, dy, dz? What would be the units of dx, dy, dz?
Cubic.
Yeah, so say meters cubed. What about rho, d theta, d phi? What are the units here? Well, theta and phi are in radians. Radians are unitless. So what's d rho, d theta, d phi? What are the units of that? Meters. I need to get up to meters cubed. I have a meters here. I need 2 more meters. How can I get meters squared? What do I have to put in? Well, no, I'm going from dx, dy, dz to d rho, d theta, d phi. I've got some function of rho, theta, and phi that has to be in front of this. I claim that you can tell me at least part of it because the units have to work. How can I get up to meters cubed from the meters? I need a meter squared. How can you get meter squared with rho, theta, and phi? What's the only thing that will give you a meter squared?
Rho squared.
Rho squared. So we know there's at least a rho squared coming into here. It's also a sine of phi, which you're not going to be able to see. So we'll stop here, but you should be at least able to see that there's a rho squared coming in.